So friends, we are into third lecture of week 1 and now we will be discussing PRA modeling part 2, that is quantification. So in previous lecture we did qualitative treatment to probabilistic risk assessment. In this lecture we will be doing quantification. Okay. So let us understand, if I have one safety system, it is called class 3 power supply system. You know, I had mentioned class 3 system will have on-site diesel generator. In case power failure occurs from the class 4 grid, these systems they take care. So the first thing which happens, if the power failure is there, the plant comes to the shutdown state automatically. No operator intervention is required. So and then the diesel generator starts and they start supplying to the essential loads in the plant, so that plant is operation is kept in a safe manner. Okay. So and the moment power supply is resumed, again the operator from the control room, it normalizes the system and then he start the plant and diesel generators are shut down and then power supply start coming from this upside power. The reason is fundamental reason is class 4 power failure, that is normal or grid power failure. Grid power is required for operating the process system, which are heavy duty systems, you know, and that cannot be operated through our diesel generator capacity. So we have this provision that AC power is either available and plant operates from offsite power, or you can say grid power, and if it is not available, then diesel generator will start and will meet the essential loads we call in just one term, and the plant will be operating in a shutdown state in a safe manner. Now, since this being a safety support system is, it is giving power supply to the essential loads or safety loads in the plant. So it is a safety support system, but the modeling procedure is same as safety system. Now what, as I mentioned you, there are two diesel generators, diesel 1, diesel 2, and these are the class 3 loads, that is emergency loads. You know, it could be motor, it could be control power supply or anything, but basically AC. So AC loads, and then we have, so this bus is called class 3 bus, that means emergency bus. Okay, and once this operates, so we want to do what is the probability of failure of power on class 3 bus. Now what will happen, either bus C and D both, and there is a tiebreaker in between. If this tie is connected, then one diesel can supply to both, diesel generator can supply to both the bus. So this is functioning of the safety support system we have here. CB means circuit breaker, DZ is diesel generator. Now, so when I say class 4 means you assume upside power or grid power, you know, and class 3 load means the loads or the motors or the controls that are operating on class 3, okay, and they are all AC. Now, when we start doing modeling for this, and what is this particular analysis is forms part of loss of offsite power. Loss of offsite power, that means power supply is not there. Offsite means outside, power available from outside. So this is one important safety support system that has to be analyzed, and its probability, unavailability rather, has to be estimated. So this is the objective, overall objective, and the failure criteria will be if both the diesel generator fail. It could be one diesel generator also, it could be two, but the plant we are talking about, or we are considering in our modeling, is both the diesel generators, that is DG1 and DG2 fail, then only class 3 power supply fails. This is the nutshell we are trying to talk about it. Now, if I make the fault tree, probably you might have seen the fault tree, or if you have not seen the fault tree modeling and all that, please refer any book on reliability and you will find these things. Okay. So if I do, so the essential feature when we do fault tree modeling is, this is a AND gate. And what does it mean here? So top event is class 3 power failure, that is emergency power failure. Okay. So under voltage on bus C, under voltage on bus D, and then only it will lead to the top event. So I will read like this: if there is a under voltage on bus C and under voltage on bus D, then only it will lead to class 3 power failure. Okay. Now, because this is a very simple fault tree which has been developed for demonstration purpose. Otherwise, there is a common cause failure here which will fail both the DGs and all that, but on both the buses, and now buses are supplied because of power supply from DG1. Okay. And if the power supply has to come from DG1, this is a DG1, circuit breaker 7. If you go and see the figure, you will find, and then common cause failure, DG1, some common cause which has failed the DG. Okay. And then under voltage on bus D will be power supply failure from bus D. That means the second bus was there. Okay. And if so, so these two failure will lead to under voltage on bus C. So DG2 failure and all DG2 failure will occur because of DG itself fails, or circuit breaker doesn't close, or common cause failure. So this is the modeling which goes into the fault tree. Similarly, similar modeling will go for bus D also. There will not be much difference. So this is a repetition. So we have two. Now we have the fault tree, simplified fault tree for class 3 power failure. Okay. Now this fault tree we have done, we have developed based on the typical consideration from the plant logic, plant component that are available, and system logic and all. But then when we do PRA, and Boolean reduction is one of the important component of. So if you use the Boolean logic, there are so many components which have come on this side, like common cause failure DG, common cause failure DG. It has come on from both the branches of this fault tree. So how to so that repetition should not be there. So for that, what is done is Boolean logic is or Boolean expressions are used to analyze this fault tree, so that we have a cut set, minimal cut set. That means minimum number of events that will comprise the fault tree. So you, after doing the Boolean minimal cut set generation, we have the fault tree over here, and this is, you will see, class 3 power failure. So it is independent failure or common cause failure, you see. And then train 1, train 2. So that means there are two DG trains, and from there, so here it is DG1 failure and CB7 failure, DG2 failure and CB8 failure. If you see the plant logic configuration, resource configuration, you will understand this. And finally, we have minimal cut set. What is the, as I told you initially, common cause failure is a really critical parameter that has to be taken care of. So what one event, that is common cause failure of DG itself, can lead to the top event. And then here we have a little relaxed, because DG1 has to fail and DG2 has to fail. So if DG1 failure probability is there, some DG2 they will directly get multiplied and they will come here. So you will find that later on this branch is not contributing in the final analysis. It is the CCF from DG which is coming in or giving leading to the main results. And so we have a cut set analysis. I have presented the result here. You can also see the Boolean logic operations on this, or probably will understand how it is done in when we do the dependency analysis or something. So DG1, DG2 failure will lead to top event. One breaker failure, other DG failure will lead to the first DG failure, second thing. So this combination will lead to this particular event, that is class 3 power failure. So this is intermediate step which is called Boolean reduction. It is same fault tree, but we have reduced the number of events for effective analysis, saving time for resources, because here there are only 5 events we have, but when we have a real fault tree, there will be n number of events, and reduction is very much required because to have a better efficiency in computation. Okay. So now what is next? For quantification, we require the data. So here we have data. Diesel generator number 1, the failure probability is this. Failure probability on demand. Okay. We have here, and then for DG1, I think it should be DG2. So DG2 failure probability, then circuit breaker 1, circuit 7, 8. We have, so these two circuit breaker we are having the similar probability. common cause failure CCF DG is 2 into 10 to the minus 3. How common cause failure is estimated? Generally, it is independent, whatever independent failure is there, you multiply by 10, because common cause are very rare thing. So, you saw the independent failure probability was here for this DG was 2 into 10 to the minus 3, 2 it has become 2 to the minus 3. This is just simple heuristics I am giving, they are much more complicated and it require a lot of knowledge and all that. So, now if with this I do the calculation with this quantified, we have data for DG1, DG, CB2, DG2, CB3, you can see here, and then we evaluate the fault tree, and you got 3.2 into 10 to the power minus 3 is the demand failure probability. You can see here this particular thing is contributing maximum here, because other things get multiplied here, simple independent thing, and from here we get a major contribution. So, common cause failure modeling is very important. Now, we have come to the second stage, that is we got the statement of unavailability of class 3 power supply system. Next step will be seeing the results, their unavailability, common cause failure, all that, the different combination, how they are contributing. We can see here that the common cause was 5 into 10 to the minus 3, and DG and CB8 was 0.. So, all the sort of, so here in this thing, common cause failure along with this DG1 and CB8 failure, they are the contributing factor, and again 9 into 10 to the minus 6, it is on lower side. So, there are 3 events they are contributing more. One is common cause failure and other things are. So, here in this particular case, even the independent DG also contributing, which is slightly away from our normal notion that only common cause failure are the major contributors, but whatever is mathematics actually. Now, estimation of class 3 power is 3.2 into 10 to the minus 3 per demand, it is available. And regulatory stipulation is that for a level, now this here itself we have one assessment for comparison where we stand as a plant. So, regulatory requirement is that the class 3 power supply failure probability or safety system failure probability bearing 1 or 2 systems should be 10 to the minus 3 per demand, and our estimate is 3.2 into 10 to the minus 3. It is slightly on higher side, but it is not a bad situation. That means some more efforts we have to do in our operation and maintenance, and we can target. Actually, it should be, ideally speaking, it should be less than this figure. That means it should go into 10 to the minus 4 range, let's say something whatever. But this is not a very unhappy situation, and I think regulators which are overseeing the plant, they might give some comment, but we will be happy generally. Okay. So, now as I told you, next step is drawing the event tree. So, in event tree is nothing but we have the initiating event, that is loss of offset power, our class 4 power failure we were telling loop, and the frequency from the plant record, it comes to 1.2 per year. Okay. So, we have data for class, we have data for primary shutdown, and here for whatever procedure we applied here for emergency power, same procedures have to be applied for other events also. For human action it will be little different, but for other system also we have to estimate their failure probability. Okay. Now, with these things we go for estimating this event tree. On top if you go it is success, on bottom if you go it is a failure. Please mind here, these are not the actual data from the plant. For simulation I have shown you this. Don't get an impression that this decay heat removal system will have a probability to 7 into 10 to the minus 2, which is not the case. It is normally in the range of 10 to the minus 5, but for demonstration and for simplicity we have been done here. So, now you see how to read a event tree. Class 4 power event has occurred, primary shutdown system activated successfully, so it will go up. If it is not activated, it will go down. Okay. And if the secondary shutdown system also, so if primary shutdown system has come, so secondary shutdown system is not required. So, a straight line going, then it requires a power supply failure, safety support system power supply. So, it is successful, then it goes here. And human action is not independent, not required, because power supply is available. And then we have a decay heat removal system if it is coming. So, we have all success. So, event accident sequence 1 is nothing but all success. Okay. Okay. So, now we got, but failure. So similarly, we have to go into the failure domain also. So failure domain is going down, then primary shutdown system has not come, and if other systems have not, then if primary shutdown system has not come and secondary shutdown system is not come, it is directly leading to accident. No more analysis branches are required in between. But if the secondary shutdown system has come, then again this tree will follow, like on top what we had. The same thing will get replicated because plant was shut down, and now other system will have the same conditions. Okay. After doing that we got a Boolean expression for loss of offsite power. It is safe. Loss of offsite power, and if decay heat removal system is not there, we have core damage, that means unsafe state, then loop. So all these events are qualified. Their consequences given whether it is safe or unsafe. Safety threat is milder than the core damage. So the different level of conditions we have to assume. That matrix is up to us what we built for one, and then finally the results. So core damage contribution from loop event. Okay, so it is coming from sequence 2, 4, 6, 8, 10. 2, 4, 6, 8, and 10. Okay, and of course 12 also. So 12 and 13. Okay. So CDF loss of offsite power, contribution of loss of offsite power to the core damage event is nothing but summation of I is equal to 1 to n. I's are given here, and then it will give you total core damage. So now let's see in the next slide. Okay, we have now quantified information also from here, and you can see these calculations when they were done. The loop DHR is 6 into 10 to the minus 6. Then other things, and for all the these are called basically accident sequences, because here it is an initiating event, here it is a safety system. So similarly, all will have a loop as the first event, because it is the consequences of loop that other events are entering into the sequences. So each one is called accident sequence. Consequences are given safe, unsafe. Unsafes are added up here, and then what we get is risk statement at level of core damage. That means inside the plant. Okay. So 6.22 to 10 to the minus 6. I told you 10 to the minus 6 is a general figure around, and this is showing again 6 into 10 to the minus 2. So if it is an old plant, these figures are also okay, because core damage frequency level should be 10 to the minus 4 for the old plant, but improvements are always required. So from even if this model is there for the old plant, which are built in somewhere in early 80s or before that, these results are considered good with additional safety measures actually in the place. So we got the quantification. Now if I want to estimate, because we want to understand various event safety system, their contribution to the total risk. So if suppose I am assuming here, if my total core damage frequency was 5.25 into 10 to the minus 5 plant per year. Okay. So if that was the case, and my loop contribution is 7.2 to the minus 6, that means 13% contribution is coming from loop. I told you earlier, we will demonstrate how the loss of offsite power is does contribute to the risk from the plant. And now we have loop major events. Okay, and then which are the system and all they are contributing, and this comes to 100% total core damage frequency. Okay, because I have not shown here LOCA, minor LOCA, ATWS, LORE, which we discussed in previous slide, but they are just for the sake of full understanding. Total our CDF is 10 to the minus 5. Now this is the 100%. If I add up, and 13% we have estimated. Why I am showing you this slide? This slide shows you a complete procedure for performing a PRA through loss of offsite power event and the support system, that is power supply, diesel onset power supply. So isn't it elegant approach to estimate the risk from the plant? They are potential risk estimates. Okay, plant is operating safely, but then this gives us confidence if we have to do any improvement modification. These indicators are available for us to have our resources in place. And now, though this slide has come suddenly, but it was I don't know whether it was part of, but this is very important thing. Documentation of PRA, the salient feature at system level, because if documentation is not there, PRA provides the documentation in systematic connectivity, interconnectivity, and rationals. How, what leads to what. So, so system analysis format should be there. System should be developed right in the initial stages of the PRA. Program for documentation, because documentation. So first, when I start the PRA, after my first project report, what I do is I develop a system for data collection and system for documentation also, because later on, and this system is made available to various stakeholders, so that they use this for documentation and there is a consistency. So it is more of a administrative and technical, to the extent that all the rational, everything, what procedure, what assumption, what method we have used, it is available. Then system analysis format, the main executive summary. So nobody will rather everybody will not read the all the report, ranging from 500 pages to 10,000 pages. Like for the executives, even main executive summary is sufficient, which is around 5 to 10 pages, and format of the report should be given, and quality attributes. I'll take a pause here. When I do a PRA, there are international documents available how to ensure quality in PSA, like initiating event selection, what are the steps you should, and if you have not taken all the steps, the quality may not be up to the mark. So suppose sometimes we are like availability of the data. Due to situation, we don't have all the data, but if we write that these attributes we have not made, we have made only 60% of the data from the plant, that goes into the record, and that defines the quality, and that in turn encourages our management in the future, so that we have rest of the data also in the plant. So this provides like external event. If I have not analyzed for external event, here the quality attribute will ask us that the scope of the this analysis, and it will present in the main result, so that people will know what are the assumption, what are the constraints in the report, and how far they have gone in it. So in maybe 1 or 2 pages, it provides the elegant results with all constraints and limitations and availability of resources, and that provides fundamental for future improvement of the model. So in this thing we have seen in a very brief 5 to 10 to 10 slides, quantification of the PRA model, inventory accident sequence modeling and their quantification, and core damage risk estimation.